In this lesson, I want to show you how to use matrices to do transformations that are rotations other than the basic 90, 180 degree, 270 degree rotations. So here, as a warm-up question, we have the point 3,4. And if we rotate it 30 degrees about the origin, where does it end up? You could take some time to just think about that geometric question and how you might approach that. So if you go over to the activity, linear algebra, day 7, they have this question here. And on the next page, you have a graph where you could actually see the answer. It ends up becoming 0.6, 0.5. And I'll show you how we get that. That's the goal of today's lesson. But what you can do is mess around with the sliders. They might give you some sort of a feel for what's going on. So if I move this back to 30 degrees, you also have the ability to move the point around. And our goal of today's lesson is there a quick way to figure out the results of a rotation, no matter what the point is and what the rotation angle is? So one insight that could help us is to write 3,4 in trigonometric form. So the point 3,4, you might remember this from earlier on. If we do square root of 3 squared plus 4 squared, we get 5, which is kind of like the R value. And the theta value is tan inverse 4/3. Which ends up becoming about 53, I'll go to the 100th, 53.13 degrees. So this 0.34 could also be thought of as 5 cosine 53.13 degrees, comma, 5 sine 53.13 degrees. Now, as far as this P prime goes, the one thing we know about it is that it's rotated around the origin by 30 degrees, which means that it has an R and theta value. And its R value is going to be 5, just like the other one was, because it's been rotated around the origin. So basically, what I'm saying is that there's like this circle of radius 5 that both P and P prime are on. But P prime's angle isn't 53.13, it's 30 degrees more. So it's 83.13. So one way of doing this question would be to just plug in 5 cosine 83.13 and 5 sine 83.13, and out would come the answer. And if you want to do this for the point 7, 2, why don't you pause for a minute and do that? Okay, so you can do this one by taking the 0.72 and converting it into, if you do the square root of 7 squared plus 2 squared, you get the R value, which is about 7.3. And if you do tan inverse of 2/7, you get about 16 degrees. There's a chance I'm in another quadrant and I have to adjust for that, but not this time. So when I rotate by 70 degrees, it ends up over here. So if this one is 7.3 cosine 16 degrees, comma 7.3 sine 16 degrees, that's P, then P prime is going to be 7.3 cosine to 16 plus 70, which is 86, comma 7.3 sine 86 degrees. And when you run that through the calculator, you get about 0.5, comma 7.3. If you go over to this thing where you can move the points around, look what happens. If I move the point to 7.2 and I move the angle up to 70, you see 0.5 and 7.3. So that's one way of doing this question. But the goal of this lesson was to learn how to do it with matrices. So transformation matrices are usually a 2x2 matrix here, because rotation is a linear transformation. Lines will stay lines when you do transformation, and 0, 0 stays at 0, 0. And all the other, like the 90 degree, 180 degree, 270 degree rotations, those were done with 2x2 matrices. Those had a lot of ones and zeros and negative ones in them. But what about this one? Well, it's not so obvious when you look at it this way. What four things have to go here, 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 and here, so that the original point, 5 cosine 53, that this is a fancy way of saying 3, 4, becomes the answer. Not obvious at all. But when you realize that the 83.13 was 30 plus 53.13, and so was the other, then you can take that right-hand side, and this is a way, this isn't going to be our process, this is a way of deriving the formula. We expand using the cosine A plus B formula and the sine A plus B formula. And suddenly we can see a lot more easily what has to happen. In the first row times the first column, I'm going to ignore this 5 for a second, I have to get cosine times cosine. So I must have to have a cosine 30 here in order to make that first term become that. And this other one, I have to multiply whatever this is by whatever that is. So, and I have to get negative sine 30, sine 53.3. Well, here's the sine 53.13. So the top right element must be negative sine 30. And down here, let me erase this to help see what's going on. So in order to get this on the bottom, when I multiply row 2 by column 1, so this term times this one is going to give us this thing, which means I have to have a positive sine 30 here, whereas this term times whatever's on the bottom here has to become this thing. So I have to have a cosine 30. So the answer is this 2x2 matrix will accomplish the rotation. And the formula is this. And that's the big formula of the day. And the nice thing about this formula is that it's not necessary to change x, y into trigonometric form. So if I go back to the warm-up question, they wanted us to rotate 3, 4 by 30 degrees. I can come over here and say, okay, I'm going to leave this as 3, 4. I don't need to actually turn it into 5 cosine 53.13, 5 sine 53.13. This formula is going to work regardless. And if you run that through, you are going to get the answer, which, what did it become? I think it ended up becoming, well, I could easily get what the answer was by coming here. So it's 3, 4. And it was a 30-degree rotation. And we see there 0.6, comma 5, which is what you get when you run this through this formula. If I want to do this on the Desmos calculator, it's actually easier to do this on the TI calculator because Desmos calculator doesn't allow you to type cosine. So I'm going to I know the cosine of 30 is 0.866 and negative sine 30 is negative 0.5 and sine 30 is 0.5 and cosine 30 is 0.866. And then I can make my other matrix be my 2 points. It's just got one column, 3, 4. And over here, I can do A times B, and out comes the answer. But actually on the TI calculator, you can put in cosine and sine, so that might be even better. Okay, well, that's what I wanted to show you for today. The big thing of the day is that there's this formula for doing rotations. It agrees with our, remember when we did rotate by 90 degrees? Whoops. When you rotate by 90 degrees, you get to minus y, comma x, and the rotation matrix was xy goes to minus y, and then xy goes, and the y coordinate turns into x. So that was the 90-degree rotation. Well, that agrees with cosine 90, negative sine 90, sine 90, cosine 90. Cosine 90 is 0, and sine 90 is 1. So this actually works for all the cases. Now there are some questions you can do on delta math where you get to practice this. Here's a practice question. Take the 0.62 and run it through, rotate it by 70 degrees. And when you do that, you end up with 0.17, 6.32. You could also verify that by going to the Desmos, this thing, and just literally moving it to 6.2 and changing the angle. .70 degrees. And you can see the answer did become 0.2 and 6.3, just as predicted. Okay, so that's it for this lesson. You can do the delta math now.